Okay, so I'm Giannis Koumoutsos. I worked at the ESRF as a software developer. I am also a knowledge engineer. And together with Wout and Nolf, I think he presented you last year in this meeting 1 year ago, the beginning of our project and our ideas on making our data a bit more fair. And fair has to do with these things that you have seen at some point, I'm sure, all of you. It's like we create so beautiful things in institutions and we need to share them, and then we get stuck with this findable, accessible, interoperable, and reusable, which actually is the end goal for all of us. And for this reason, every institution almost has a data portal. It's a place where we publish our results. And of course, we're trying in that way to make them findable and accessible. But we also have the Nexus standard, which is started many years ago, trying to make this data that we publish one way or another interoperable and usable by providing a common format, let's say, a common structure that our software can then use. So we have a lot of things that, as we came to understand lately, is that we miss a lot of metadata traveling from our beam lines up to the data portal, and then they would really make the difference in reusing and understanding the things we actually publish. So yes, the Nexus standard probably is well known by everybody. So it's a kind of structure. It's a structure that goes down. It's a tree. And then it's accessible by machines, by the software we all develop in our institutions to get into there and extract all the data needed to process the data. And we have always nice graphs. But still, it's only the structure. It's only a structure in the disk. And as I came to understand, because I'm not a scientist, I came to understand that it's not being used so much, even in the ESRF, that they want to do that. This is a nice picture that Wout created for the last presentation. So yeah, we can see here that we are trying to get to fair data, but we actually, up until now, we are not even having in our metadata the technique being used in our experiment. Even if we do sometimes the technique, we cannot easily publish it. And if we publish it in our data portal, to travel all the way from the bin line when the experiment finishes up to the data portal, it's like usually a string, something that has some meaning, but not for all of us. And surely we don't have every technique. We just say fluo, and we try to understand what the experiment did exactly. So in order to walk this path, we understood that we have so many things in order to describe an experiment that we were disappointed. And there are so many that everybody is disappointed by that. And we thought that we should start by the technique to find a way to describe our techniques. And then these techniques can follow our experiments in our data portals, in our in ICAT databases, in HDFI files, and give some meaning to the actual data. So we started like a year ago, or more than a year ago, with Renaud in ESRF, and we created a flat list. I was there back then, and we created a flat list, like an Excel sheet, holding all our techniques. And if you can see here, probably you can see my pointer, my mouse moving. It's a connection to PANET, because at some point we discovered that there is a structure trying actually photon and neutron experimental techniques. It's PANET, and they're trying actually to do what we were trying to do. And we gave just a mapping between our techniques and PANET techniques. We saw pretty soon that this is not enough. What we were doing cannot be used. It's not explorable by any machine. It was only for human use. It would need to be updated every now and then, because beamlines change the techniques they apply, or the beamlines even close, or they move. So we went to the taxonomy layer, where PANET is a kind of a taxonomy. Taxonomy, you all probably kind of understand what's that. You're trying to give a structure, a class, subclass structure to your data. And actually that was what PANET did. I'm running a bit with all these because they're kind of known, I suppose. And about to show some of these things in the last presentation. So, and here you can see PANET actually that has a reflectometry. That's your thing. But PANET is like a taxonomy, so they have kind of a structure. I will show it to you if we have time later, this taxonomy that they have, creating a subclassing hierarchy, let's say, where they are trying to put all their techniques, but their techniques, imagine if you have a tree that goes down, all these high-level classes need to be mapped, need to have as a subclass reflectometry, exactly all of them. If one is missing, then reflectometry is losing some meaning. And I think bad things can happen, so we followed a different approach regarding that. Because I came into the team and I explained to them that ontologies can actually give us a hand. More than ontologies, let's move totally the whole project into the knowledge engineering space, where more tools are available for us to do our work that Nexus probably didn't know back then, like many years ago, 20 even years ago. So what we actually did is we were trying to find a way to describe what we want, because data have to speak on their own. And for that to happen, they should have meaning, and ontologies is a way to give meaning to data. We will see how this can be done later, but it all boils down to one thing. You need more descriptive power. You need more power to describe things, but not only to have a subclassing hierarchy that gives you some information, but actually doesn't give you the exact meaning of what we are trying to describe. So in order for that to happen, we needed a next level in description power tool, which is logic programming, actually, in the field of description logics, mathematical models that actually are trying to grasp meaning out of language. And it all started, I will try to show you how this all became to be. So, sorry, let me move this down, kind of. So it started at some point because I was trying actually to do what? To go into our file system and the HDFI files and actually infer, try to see our HDFI file and see what technique is used in this experiment. We had zero clue of what we were seeing at, but Wout was kind of expert of these beamlines. He used to work in these beamlines as a scientist. So he had some clue and he created this script that if you go down, he gets an instrument and then the instrument name and then creates classes, iterates over positioners. Probably this means something to you, not so much to me. Moving positioners, and then what he was trying actually to do, because I was there when we were trying to develop this, he was trying to parse the HDFI file, get all the info from there, and according to some things like the units being used, or like in these cases, it seems that this is an energy scan because of that. This is a translation scan because of that. And he was trying to create all these small scripts to get to the final thing, which is the infer technique from scan info. So from the HDFI file to actually infer some techniques. And that was because he actually was an expert in this specific beamline we were trying to explore. So pretty soon I got this example from him and I showed them that what programming is in another way with ontologies is actually this. So you have, it's a very small ontology, just as a proof of concept to start working with ontologies. You have all the technique, all the things there that were in the script. You saw them in the script. Now it's in the form of the ontology, because what he was trying actually to do is give definitions, like these definitions. So what we are looking now is Protege is a tool that we use to develop ontologies and reason over them, reason about the structure. So you see that I'm trying here to give some definitions that an energy what is fluorescence XAFs? I don't even know what's that, but I saw it in the script. I copy paste concepts only, and I gave these descriptions. And then if you go to individuals, let's say is like when the thing you saw classes is the structure of your knowledge base, which kind of a database, and the individual is actually the lines you put in there. So I started putting some things in there, and you will see here that we have an experiment that has a positioner of this type, and you can go and see that this positioner uses as units DEG and other things like that I saw in the script. And how do you see what happens? You just start your reasoner, if you see here. So an ontology is kind of a program that you can start a reasoner and goes through all your thinking, the way you define things, and draw some results, some conclusions out of all this knowledge. So if we start a reasoner here, we see that in yellow, this kind of thing is a fluorescence tomography now experiment. And experiment 2365 with only these two things was able to infer that is a fluorescence tomography, exactly copying what the script did. So if in this knowledge base you just parse all your files with the same script, and instead of having Python scripts to create to draw some conclusions, you have this, you can actually infer the technique. And then from that, we started thinking that we can actually use this thing, and we went on to build our ontology. Okay. Let's get back to the presentation. So yes, so all this process, it requires some knowledge acquisition steps. You have the expert, scientist, more scientists is even better. And you try to get the knowledge out of them, what they mean when they say some words, some keywords. And these keywords then have some definitions that you put in your ontology, and the ontology and the reasoner with working with the ontology can infer from many things, as you will see as we proceed. Then, of course, after knowledge acquisition, we have the representation. You create your ontology, and the reasoning mechanism comes to run, actually, your knowledge. These are pretty much the standards we already use, and some more by now. We won't go through that. It's enough to understand that ontologies have a whole stack of things. It's a very big field. It's not ontologies anymore. It's the semantic web that can use all these technologies, protocols, and languages. So we started developing our ontology, and I will show you 4 things that we focused on. First of all, we try to use some building blocks to actually define our techniques, not just subclass them and hope that from the subclassing somebody will infer the meaning. We wanted the actual definition. From this, you will see that we can create the structure of a tree automatically, because the reasoner will do that for us perfectly. It won't miss a thing. Actually, it will help us when we have something wrong. We focused on differential definition, differential meaning, which means we started by XAS and put it like a spectroscopy, and we put it the things that XAS is about, and then all the subclasses of XAS. We didn't say it's a subclass. We just added more building blocks to describe, to differentiate, let's say, from XAS all the other techniques that are very close to XAS, subclasses or superclasses. And by that, in that way, we gave meaning by the differences all these things have between them. And we try to connect, of course, with any ontology in our domain. We are still in progress with that. We are connected to Panet and Nexus ontology, but we are expanding on that to connect with other ontologies, because in this kind of semantic web, the web actually gives meaning by connections. The more connections you have, the more connections with other ontologies and fields, the more meaning you have to your techniques or to whatever you are building. So this is kind of things that I can show you. If I cannot show you them live, I will try again to go to live. Yeah, this is then the ESRF. Can you see it? It's. I hope it's big enough.
It's small, but it's readable.
Okay. Because it's a Java tool, I cannot zoom in anymore. So you can see here that actually this is kind of XAS, and this is the kind of the definition we gave. You see that for us, it's an experimental technique that, and what else? It's the specific characteristic measures as a function of detection, as a function of incident energy, and this is this here are the building blocks we used on the right side, and this is the connections, the object properties. It's actually the way you connect your classes between them, measures as a function of, and some object properties like that. You connect in order to create, actually, if you see it, it flows like a sentence. So ontologies are very close to humans because of that, but this is actually executable. The code you see here is executable by machines instantly. The minute you write it, they can you can throw queries on that, or you can unleash your reasoner. And actually, you can see here that because it's in yellow, the reasoner already has inferred some subclass, that the XAS is subclass of all these things. You can also see here that we connected to Panet. This term comes from another ontology, which is the photon and neutron ontology, that has a lot more techniques because it's not for the ESRF only. And you can see here that our approach was to actually create a flat list of techniques, like having an Excel sheet. But when we unleash the reasoner and go to the inferred, what the reasoner thinks about our structure, you can see here that actually there is a structure that the reasoner knows about and that the machines are able to understand. So all these techniques here that you don't see in a tree, they are not yet defined. So there is no definition yet. We just use them in our beam lines. And how do we use them? We use them with this Perl, this unique identifier. That's why it's the first step, why you should build an ontology. It gives you a unique identifier that actually holds in there the keyword you want to use, the technique you want to use in this case, along with the definition and all the other things you can do. But then you can take this URI, and we are already doing that, as I will show you later, and you can put it in your data portal, whatever you want, and then your experiment is annotated with data that are unique, and everybody can find them by just clicking on that and going to the appropriate URI. So if you see here, everything under the tree of X-rays, we use these X-rays to put it when we don't have a technique. Right now we have most of them, so probably X-rays will never be used in our beam lines, but at the beginning we used more general terms since we were still developing. And you can see here that X-ray absorption spectroscopy coming from another ontology is in our structure and is actually equivalent to our XAS. And you can see here as well XAS including this. So what happens here is that we have all the ontologies together and we create our structure by the definitions we give. Because if you go here, if you go here, you see that there is a definition. And actually, this definition includes XAS, or X-ray absorption spectroscopy from PANET, plus the differentiating building block that we apply to it. And so the reasoner is able to create this kind of tree. So in this you can see here some of the tools we have in this approach. That's it. A lot of tools. We can execute direct queries. So if you can see here, it's like a Sparkle thing. It's actually a way that you can query your knowledge base as if it was a database. This just gives you all the techniques, but you can unleash very complicated queries, like if you had a database. And you see here that there are different kind of techniques that are closer to humans, like description logic techniques. And you can just write what is XAS and has this characteristic and gives you immediately the equivalent class. Again, all the superclasses from that, you don't even know they exist. The minute you create your ontology, you don't define them. They are inferred. The reasoner tells you about all the structure. And of course, what are the immediate subclasses of this thing that you put it here, which is XAS with a building block. If we just delete the building block, for instance, and we again execute, we get other things like we expect it to be. Equivalent class now is XAS only. So that's pretty much what we can see here. I don't think we need to go any further on that. It gets somehow complicated. Okay, and then let's get back to our presentation. Right, so you already saw these things kind of live. Just to tell you that all this process went through a few steps, and these steps included like defining simple things like this one. I hope you can see it. So it's atomic core excitation end, which is not a sentence. It's not something that you can really run a reason on top of that. But it was our initial process, so it's the way you build your ontologies. You first collect all your building blocks together, try to define things raw, as in this case. Later on, you can move to more complicated things like this one, which has more complicated descriptions and building blocks and connections that can cooperate with other ontologies, like this term coming from PANET, as I told you. And later on, you can move to when your ontology is mature enough, you can move to actual definitions, give the comments, graphs, whatever you want as references, and create the appropriate definitions that can be used by LLMs or any kind of AI. It's a lot easier for them to dig into these things and understand sentences instead of structures, abstract structures. And the goal behind all this actually is to have a common word, a common vocabulary, let's say, at the beginning, between all institutions. So PANET in this graph stands in the middle, because if we can have just a connection to PANET, everybody, then it's like having the ESRF ET directly mapped to other ontologies in the domain that may be developed by other Sankotschool institutions. This is actually the added value of ontologies. After a while, if this is connected in not so difficult way, as you saw, just by putting the same concepts as equivalent to the concepts you defined, then you have all this structure that you can explore and exploit. And of course, you have the Nexus ontology that's now almost done, and we actually connected the ESRF-ET with Nexus by now. And we are exploring more opportunities to connect directly to Nexus concepts. And then we can easily have scripts like the one I showed you, because Nexus terms will be directly connected with technique, and the reasoner will be easy for the reasoner to understand that this kind of, if you see some description in Nexus, it uses this technique directly. So the short terms now go for the ESRF, but we are trying to convince any other institution to come with us in this trip, is to actually publish these IRIs, as I described you, in our ICAT, in our data portal, but also in our HDFI files. And actually, we have done that. And I'll show you a print screen of some beamlines already publishing these IRIs. This, for instance, is ID 15B, I suppose, where you can see here, it's very small, that we are already in the position of publishing concepts directly from the ontology coming into our data portal, so providing metadata. Midterms in our project is like to go a bit further on that and actually create a bigger ontology, like the ESRF FAIR ontology. We already started working on that. The FAIR ontology will include more things, because now we are looking just at techniques, but in order to have real FAIR data, we need to have a lot more things like beamlines, scientists, publications, proposals. All these terms are actually related to time, because beamlines start and stop, experiments start and stop, publications are being published in a specific date. All these things, if you put them in the timeline, they give you context. So you can write questions like, after a while, it's one of our questions, targeted questions that our ontology needs to be in position to answer, is like, I have this kind of, you unleash an LLM to go through your text to a publication and find some scientist there and finds an experiment maybe. And then with all this, you create a query to our knowledge base and say, I have this scientist. I don't know if this scientist was in the beamline, working in the beamline, or he is the principal scientist conducting the experiment, but I still have these ones associated with, and the knowledge base will be able to answer that probably the data that are in this publication are experiment 1, experiment 3 in ESRF, and experiment 300 in DESI, because it can easily understand these concepts now, and it can go through that and search. And this is the big difference with LLMs and vector searches that are, and Elasticsearch, for instance, which is great. But this one is definite. It's like what it finds is for sure. There is no hallucinations. It's a structure, and then it's like querying your database. It's not like imagining things or trying to find some relation in things like vector databases are trying to do. And the long term, after all this, the goal, and probably I will finish here, it's like we're trying to have all this in multiple facilities, because actually this Sparkle that I didn't talk about, but it's the query I showed you in Protege for just a second. It's like it can run in federated fashion, which means what? You can have the same kind of vocabulary or connected to PANET, it's the same, connected to a common ontology, and then you can write your query like writing a SQL query, and this query can, at the same moment, draw data, knowledge, let's say, from all institutions that have this endpoint. So you don't go to have through all the data portal or to download data and search, filter, then go to the next institution, search, filter to find them in a specific kind of experiment, or to answer just a query. I need to perform this kind of experiment. In what synchrotron should I go? this kind of queries would be very easy if you have this kind of structure. Just to finish with that, is like ontologies and semantic web and fair data all have to do actually with answering questions. This is kind of the questions we first wrote before started working on the project, and we would like to have a way to answer them after finishing the project, like where do I go to perform an experiment, or more complicated ones, and for this one we need a lot more ontologies in order to get there. But I want to find which pigments 20th century painter used in this painting, which technique should I use. These questions actually came from scientists, and we were trying to see what kind of data, knowledge, but it's kind of data we need to collect, what kind of ontologies we need to connect in order to have answers for these complicated, I would say, queries. So yes, a bit out of the context, I suppose. That was fair data in ESRF. Thank you for your